Good day, everybody, and once again we are back together, still looking at that IEB paper from 2018. So yeah, join us. I'm sure that you've been, enjoying the incredible lessons that we've been trying to help you with as you prepare towards your final exams. And by the way, if you haven't subscribed, please just make sure that you're part of the family. And for those of you that may need assistance with either mathematics or physical science, please, why don't you just send me an email? And my email address is info@mlungisinkosi.co.za. All right, now let's get right into question 7, which has to do with electrical circuits. Right, so it says a battery of EMF 6 volts and an internal resistance, is connected in series in that case to two resistors, each with a constant resistance as shown in the diagram. So there's our two resistors there, they're connected in series. Okay, we know the same current is going to pass across each one of them. Okay, so they say the current I1 is supplied, okay, by the battery, which is 0.6 amperes. Okay, now they take the very same circuit, the very same resistors rather, and they put them in parallel with each other. They say the same battery is now connected to two resistors also at constant resistance, okay, of R, connected in parallel as shown in 7b, right? So of course now they connect them in parallel as now the current that is supplied is 1.5 amperes. Of course, once we change that the arrangement of our resistors, it's obviously going to affect the effective resistance of the circuit, and ultimately it's going to affect the current, right? Okay, so the first question, they want to know the definition of resistance. Okay, and we all know that resistance is just a material's opposition to a flow of current, right? Okay, and the second one also has to do with the definition. They say define EMF. Oh, guys, I'm so lazy. Of course, I'm not going to write all of that down. Perhaps you should know this by now, okay? You should know your definitions by now. And we say that EMF is the total energy per unit charge that is supplied by the battery. Okay, right, now let's move on to our questions. Now they say consider the circuit in 7a. Remember, it's this circuit over here, right? And they want to know, they say write an equation to express the EMF in terms of I, internal resistance, and obviously big R. Now, if we just remember, when we use the EMF equation, we say, well, EMF, we know EMF is equal to I into R plus the internal resistance, right? Okay. Now, when we use this, remember, and for those of you who haven't watched my videos on electric circuits, please go and watch those so that you can understand what we're saying. So when we use this equation, we know that E is obviously the EMF. So which current do we use here? It's always going to be the total current, okay? Keep that in mind. And which resistance do we use here? We use the external resistance of the circuit. Now, if you think about this here, they said that the EMF is 6, okay? And we're given the total current to be 0.6 amperes. That's the total current in our circuit. But if you think about R external, remember it's going to be the effective resistance. In this case, it's going to be these two resistors here. Okay, so they are effective or total resistance. It's going to be R plus R, and so that will give us 2R. Okay, plus the internal resistance, which we are not given there, and that's going to be the expression. So they wanted us to write this expression here. Okay, actually I should have numbered that 7.1.3 so that we know what we are answering. Okay, so the second one, remember they just said for 7a, they say consider the circuit in 7b, okay, and write down an equation to express the EMF in terms of, okay, so they want the same thing, but only this time for the second circuit. Now, just to keep in mind, ladies and gents, okay, we're going to actually do the very same thing here. However, okay, again, same equation, R plus small r. But now remember that your resistors are in parallel, right? So what does that mean? It means that your effective resistance, so I'm just going to do it, just calculate it here on the side. So your effective resistance, we usually say 1 over R parallel is equals to 1 over R1 plus 1 over R2. Okay, so to find our effective resistance, it's going to be 1 over R parallel. So 1 over R plus 1 over R. Okay, so because our denominators are the same, we're going to say, well, in this case, this is the same as having 2 over R. But remember, that's the inverse of the parallel resistance. And so it means that R parallel would be equals to R over 2. So we just invert that so that we get the effective parallel resistance. By the way, when we've got two resistors, I always prefer to just simply say, take the product over the sum, right? So in this case, R parallel simply becomes R, the product, okay, R times R divided by R plus R. So in this case, what do you have? You've got R squared divided by 2R, and what do you end up with? So 1R will cancel one of them, so you end up with R over 2. So that works so that you avoid that having to invert at the end, I suppose. Yeah, just simply say product over the sum. Right, so in this case, we've got our EMF. Remember, the EMF stays the same, okay? But what changed? The current changed. We've got the total current, and this time it's 1.5 amperes. What's our total resistance in this case? That's going to be R over 2, okay? And our internal resistance, by the way, remember, it also remains the same, okay? Right. I'm not sure why I can't get these camera settings to be what I want them to be, but nonetheless, I hope that you can see. All right, so right now the next question, they say use the equations in 7.1.3 and 7.1.4 to calculate the resistance of R. All right, so if we can call this one equation 1 and this one here equation 2, okay? Right, now you think about it. Both equation 1 and equation 2 are equal to the same thing. So if both of them give you EMF, which is 6 volts, what does that mean? It means both equations are essentially the same, right? So if their left-hand sides are equal, both of them equal to 6, so will be their right-hand sides, right? Actually, you know what? Let's do it in a different way. In fact, let's take equation 1 and let's try to solve that equation 1. Try to simplify it. Okay, so I'm going to say, well, for equation 1, we know we had 6, but now let's say this is going to be equal to 1.2, 0.6 times 2. That's going to be 1.2 R, okay, plus 0.6 R, okay. Yeah, so if I take or try to solve, in fact, you know what, I think I've just just made it more complex for myself. What we could have done is just to simply eliminate R there and make it the subject of the formula. Okay, let me do that. Okay, let's do that. So I can divide by 0.6. Okay, yeah, you're walking with me through this juggle, this jungle, that I'm in. Right, so you divide by 0.6. So I'm going to say, well, 6 divided by 0.6. I'm going to say 6 divided by 0.6. Okay, that would give me 10. All right, and so I've got 2R plus small r there. That's from equation 1. Can divide both sides by 0.6. It cancels that one out. and this one 6 divided by 0.6, that will give you 10, and you've got this 2r plus r. So that means if I now want to make r the subject of the formula, it means r will be equal to 10 minus 2r. Okay, right, so you can call that equation 3 if you want to. So what I'm going to do is I'm going to substitute equation 3 into equation 2. Okay, so take it there. So 6 is equal to 1.5 into, now you remember we had r over 2 there, plus, now my small r, this is going to be 10, small r would be 10 minus 2r. Okay, and all that is left is for us to just do some mathematical gymnastics. Okay, right, so I can divide both sides by 1.5. Okay, so that cancels that over there, and then add, now I've got two in this case terms that are alike. They've got r, both of them, so I've got r over 2, okay, minus 2r, and that would give me yeah, so that would give me minus 3 over 2r, right? Yeah, you can try that out. So that would give you minus 3 over 2. So this is the same as saying half minus 2. Okay, that would give you a negative 1 over 1 over 2. So minus 3 over 2r plus 10, right? In fact, I should have just even removed the bracket, and 6 divided by 1.5, that should give us 4. Now, if you take the 10 to the other side, you'll see that this becomes negative. Okay, so that would be minus 6. So 4 minus 10, that would be minus 6, which is equal to minus 3 over 2r. And what would be our value for r? So you can divide by both sides by 3 over 2, or negative 3 over 2, that is, or just simply multiply by the inverse. Multiply that by 2 over 3, negative 2 over 3, and multiply the, what you do on the right, you do on the left, minus 2 over 3, and you'll realize that cancels that, that cancels that, so you're left with r, and you'll realize that r is equals to 4, right? So it means that our resistance will actually be 4 ohms. All right, okay, so that is how we will solve that there. I'm quite certain you could have probably done that in a much easier way. I don't know if there is, but yeah, we try to eliminate one of the variables, and we solve simultaneously. All right, let's go to the next question. Okay, they say define power. Oof, what a lot of definitions here. Remember, power is the rate at which work is done. Okay, so we say power is the rate at which work is done. Now, they say calculate the power dissipated by one of the resistors, resistor R in 7B, so which is right here. Okay, so I want you to please note. Okay, if you don't mind, I'm just going to bring this over to this side and continue. Okay, so I want you to please note, when it comes to power, you need to always make sure that you use the right voltage, okay, or the right current. So if you think about 7B, okay, we don't know what the voltage is there, and please, I ask, don't dare say that that is the EMF, okay, that the voltage there is equals to 6 volts, because remember that the external voltage there will be the difference between the EMF and the internal voltage, meaning the voltage that is or rather the voltage across our internal resistor, right? So in this case, we now want to find out what would be the current that passes through. Okay, I'm going to use actually the one about current. So I want to find the power. So I'm going to say, well, it means the power, now please stay with me, is equals to I squared multiplied by R. Okay, of course, the other the formulas, when you calculate, you'll say V times I, but I'm trying to avoid voltage because then I'd have to go through the step of actually finding the voltage and all that. Okay, right. So I just want to find out what is the power dissipated. Remember, now we know what the resistance is. We just found it in the previous question. We said it's 4. Okay, so we want to find out what the power is. Now, the moment that we have current there, what do parallel resistors do? They actually divide the voltage, the current, that is, right? But when they divide current, how are they going to divide current? Of course, they are going to divide it equally this time. And the only reason for that is that those two resistors are equal resistors. Okay, so in this case, we're going to say, well, so therefore, what's the current across one of them? It's going to be a half of that, which is 0.5. So therefore, power would be 0.75, okay, squared. And we're going to say multiply that by 4. And let's find out what that is. Squared times 4. And we get a value of 2.25 watts. 2.25 watts. I want you to please note, of course, you could have, all right, you could have calculated that power by finding the voltage, but you would have needed to find, okay, so what I could have done in the previous one, let me just show you quickly, all right, so what I could have done is I could have said, well, I know what the current was, I know the resistance, and I know I know the total current. So remember that our effective parallel resistance would have been R over 2, so it would be 2 over 2, which would give me 2 ohms, right? So this would be the effective parallel resistance. So what you could have done is say, well, I can find out what the voltage is, okay? The effective, or rather the external voltage, it's equal to I multiplied by R. So you could have found our current was 1.5, our total resistance was 2, so that gives us a voltage of 3 volts. You see why I was saying that would not be the same as the EMF, right? So our voltage would be 3 volts, right? So remember, in parallel, voltage is the same, right? So it means that the voltage across R would be the same as the voltage across the other R, and it would be the same as the voltage across the effective resistance between the two. So in this case, I can simply say I can calculate power. Power would be voltage multiplied by current, okay? So I could have said, well, this is 3 volts multiplied by, now remember, the current on each resistor is not 1.5, but it is rather, the divided voltage, and it would be 0.75, okay? And in this case, that would give you exactly the same value, which is 2.25 watts. Okay, so you could have approached it that way. I still find this one a bit more, more efficient in answering that question. All right, I hope that is clear. Okay, of course, you could have also used P is equals to V squared over R. I'm not going to go there. Okay, when you found the voltage, and it was going to give you the same value. All right, now let's continue. Okay, this is the the continued portion of it. Now they say a third resistor R is connected in parallel with the resistors in 7B. So now we've got 3 resistors, right? Okay, and they say state whether the reading on the voltmeter would increase, decrease, or stay the same. Use a suitable equation to help you explain your answer. Yeah, so they really love these kind of questions. So what I'm going to take you through it, okay? So want to know what would happen to the external voltage, right? Okay, so first of all, I want you to listen carefully in this explanation. So first of all, anytime that you make a change in the resistance, okay, or anytime that you make a change in the circuit, okay, the first thing that you're always going to do is check how is the change that I'm making going to affect the effective resistance. Okay, right, please just stay with me so that I can explain this part quite nicely. So the first thing that you check is how is it going to affect resistance. Now I want you to think about it. When you add resistors in parallel, right, essentially what you do is you actually decrease the effective resistance. So I want you to think about it, okay? If I were to have two resistors in parallel, okay? If I were to have two resistors in parallel, let's say they are both 10 ohms, right? So if they are both 10 ohms, the effective resistance would actually be 5 ohms, right? You'd say 1 over 10, 1 over 10, and that would give you 5 ohms. But if I were to add another resistor in parallel, right, 10 ohms, now the effective resistance would be 10 over 3. Your effective resistance would now be 3.33 ohms, right? So I want you to note, if I were to add another one, okay, the effective resistance would now be 2.5 ohms, all right? So the more resistors you add in parallel, what that does is that it decreases the effective resistance. I hope you've been able to see that trend, right? Now, what happens to current? Current would increase. Remember, I is equals to V over R. Don't worry, we're getting to the answer, okay? Right, so I want you to just know how to explain that. So what have we done? We have decreased the effective resistance, and so what happens to current? Current will actually increase. All right, so by adding a resistor in parallel, it means that we are decreasing the effective resistance, and so we are increasing the current. That's according to Ohm's law, right? Now I want to try and so let's say E is equals to I into R plus small r, but let me just put this equation in a different way. So E, the EMF, is equals to V external, okay, plus, so if you say I times R, remember that's total current times the effective resistance, so that would give you V external. But this one would also give you, we say it's V loss, so you can call it V internal, right? But what we want to know is how will this guy be affected. So let's try and rearrange this formula. So V external would be equal to, right, if I take this to the other side, it would be EMF minus V loss. But also let me put it this way, V loss, remember, that's I total multiplied by R internal. Please, I want you to stay with me because I want you to understand this quite nicely. We want to know what will happen to V external, right? Now, I've just explained to you that by decreasing the external resistance, what have we done to current? Current has increased. Now, please stay with me. We have now increased the value of current. So current increases, all right? So if the current increases, what happens, right? My V loss would also increase. All right, it means that the voltage across the internal resistance would also increase, right? Now, if this increases, remember EMF stays constant. If the V loss increases, yet the EMF stays constant, guess what's going to happen to our external voltage? Our external voltage is going to decrease. I hope that I've been able to explain that quite nicely, such that you understand. Remember, every time we change, the setup of our circuit, when we rearrange resistors, we must always ask ourselves, how is it going to affect the resistance? So we said Effective resistance decreases when we add a resistor in parallel. So what that does to the current is that it increases the current. Okay, so then you go to this equation here. You said V external, or EMF, is V external plus V loss, which is the voltage across the internal resistance, right? But we know we've increased the current, V loss would also increase, but because EMF stays constant, it means that our V external will decrease. I hope that makes sense, ladies and gents. So our answer is it will decrease, okay? And we've used this equation to kind of explain that. Okay, I hope that makes sense. All right, let's move on to just the last questions. They say two different bulbs, that is A and B, are connected in parallel to a potential difference of 12 volts. Okay, so we've got a different set of circumstances there. So they're connected in parallel, right, to a potential difference of 12 volts. They say bulb A glows more brightly than bulb B. Now, I want you to please think about it. Okay, I'm just trying to save some space here. Okay, so there it is. We've got two light bulbs. Okay, and they are connected in parallel to each other. So there's our light bulbs. They're connected in parallel to each other. Now remember, in parallel, we know that voltage is the same. You must keep that in mind. So the voltage across this guy would be 12 volts, but it means that the voltage across that guy would also be 12 volts as well, right? So if there's to be any difference, it's not because of the voltage, right? So in this case, they tell us that bulb A glows more brightly. So let's say that was bulb A, okay, and that was bulb B. So if this guy is glowing more brightly, and remember, glowing brightly, or the brightness of a bulb depends on the power across it, right? So the power is not due to voltage in this case, because voltage is the same. So if you take the equation P is equals to V times I, right? So if bulb A glows brighter, it would be obviously due to more current being able to pass across that bulb there, right? Okay, we'll get to that as we answer the questions, but I just want you to see that. So it would be, the voltage is the same, so it means that the current there should be actually greater. Now remember, in parallel, how do I get more current to pass there, right? How do I get more current to pass there? It means that the resistance of that light bulb should actually be smaller, right? All right. Yeah, let's now answer the questions that they actually asked us. Now, in this case, they say define potential difference. Okay, remember that potential difference is the work done. Okay, this comes from that formula there. So potential difference is the work done per unit positive charge. Okay, so it's the work done per unit positive charge. All right, they say for the following questions, right, answer bulb A, bulb B, or neither one. Okay, they say which bulb has the greater potential difference across it. Okay, of course, we did say that the potential difference for both of them is exactly the same. So the answer there is going to be neither. Okay. They say which bulb carries the greater current. Okay, and I've shown you there that because it's glowing brighter, bulb A should have actually more current. All right, and the last one, so that would be bulb A. And the last question, they say which bulb has the greatest resistance, right? And I've shown you there that, remember, for there to be more current across A, right, it means that it has to have less resistance. Okay, so the one that has a greater resistance should be bulb B. Okay, right, I hope that makes sense, ladies and gents. And essentially that's our 28 marks, and we would have scored ourselves that 28 marks in such an easy and remarkable way. Right, and yeah, so that is it. That's how the cookie crumbles. All right, so if you haven't subscribed, please just make sure that you do the right thing. All right, and please, guys, tell more people about our channel, okay? And yeah, just add to our numbers. We're growing, and we want to make sure that we give you good content all the time. Otherwise, I'll see you guys next time. Sharp, sharp.